Today's lesson begins with a real slam dunk classic among mathematical brain teasers. If you've never seen it before, I strongly encourage you to try solving it before I reveal the solution. Have a look at this arrangement of 9 dots. Your task is simple. Connect the 9 dots with 4 straight lines, but without lifting your pencil from the paper. To illustrate what we have in mind, here's an attempted solution. Sadly, that solution requires 5 lines. That's one too many. So how can we do it in just 4? As I said, you should try this puzzle yourself if you've never seen it before. Pause the video here and give it a shot before continuing. Were you able to find the solution? Let me show you how it's done. It's obvious once you see it, but seeing it is no small task. People are often unsuccessful with this puzzle because they tacitly assume that the lines must stay within the box defined by the 9 dots. But I never placed that constraint on you, did I? This is illustrative of a difficulty people encounter in problem solving. Failing to see a creative solution because they impose unreasonable restrictions on their thinking. Sometimes, as here, the restriction can seem so obvious and natural that you may not even realize it's an artificial restriction at all. Recognizing these unnecessary constraints on what's allowable is a first step toward becoming a skillful problem solver. Solving the puzzle with 4 lines is a nice accomplishment, but it's possible you're still unduly restricting your thoughts. You see, it's actually possible to connect the dots with 3 lines. The key is to realize that these are not abstract mathematical points that have no thickness or area. These are actual physical circles on a page. That means we can use a solution like this one. I said you needed to connect the dots with 3 straight lines, but I didn't say that each line had to go through the center of each dot. I'm sure you've heard the expression thinking outside the box, meaning thinking in creative and unrestrained ways. This expression was likely inspired by this very puzzle. Today's lesson will be devoted to precisely this sort of thinking, and I have a number of puzzles for you to help make the point. Here's another warm-up for you. When I first saw this one, the solution actually made me laugh out loud, since my own restrained thinking kept me from seeing the solution. Maybe you can do better. The problem is to take 6 matchsticks and to arrange them so that they form 4 triangles. That's it. Making 2 triangles with 6 matches is rather easy, since we just do this. We could also make 2 triangles with 5 matches like this. If we're willing to stretch things a bit, we are thinking outside the box after all, we could try something like this. That sort of makes 4 triangles, the 2 big ones we started with and the 2 small ones sliced off from their tops, but we're going to declare this sort of thing against the rules. We're going to say that the matches are only allowed to meet at their ends. They can't cross each other. Now have a go at it. Take 6 matchsticks and arrange them so that they form 4 triangles. Pause the video and I'll present the solution when you're back. Okay, here's how it's done. The key is that I never said that all 4 triangles have to lie in the same plane. That means we can simply arrange them in the form of a pyramid, like this. The base of the pyramid makes 1 triangle, and the sides make 3 more. I just love that. It seems completely impossible until you free your mind from unnecessary restrictions. So-called matchstick puzzles, like the one we just considered, are an almost bottomless pit of examples for outside-the-box thinking. Let me show you a few of my favorites. Here's an interesting configuration of matches. If we think in terms of Roman numerals, this configuration displays the false equation 1 minus 3 equals 2. Can you move 1 matchstick so that the resulting equation is true? Take a moment and give it a shot. Let's see if you got it. To make 1 minus 3 equals 2 into a correct equation, we take 1 match from the equal sign and use it to make the original minus sign into an equal sign. This produces the correct equation 1 equals 3 minus 2. Along those lines, here's another absurd-looking equation. This one says that 8 minus 3 equals 3. Once again, your challenge is to move just one matchstick to make it a true equation. Actually, there are at least 3 possible solutions to this one. Put me on pause to see if you can get 1 or 2 of them. Okay, let's look at 3 solutions to this puzzle. One solution is to remove the crossbar from the 8, use it to turn the minus sign into a plus sign, and thereby transform the equation into 0 plus 3 equals 3. Alternatively, we can turn the first 3 into a 5 by shifting over one match. This produces the correct equation, 8 minus 5 equals 3. Come to think of it, we could instead have used the same trick on the second 3, thereby producing the equation 8 minus 3 equals 5, which works just as well. Here's another matchstick challenge. Have a look at these 3 triangles. Can you move 3 matches so that 5 triangles remain? Take a moment to figure it out. So, how do we move 3 matches to leave behind 5 triangles? We do it like this. We now have 4 small triangles and 1 big one. Remember, we're thinking outside the box here. For our last matchstick puzzles, here are 5 matches arranged to look roughly like a giraffe. Your challenge is to move just one matchstick in such a way that the resulting arrangement of the matches still forms the same giraffe. The new arrangement might be rotated or flipped relative to the original version, but it must be the same giraffe nevertheless. See if you can do it. Did you figure it out? We can move one match like this. The giraffe has now been rotated by 90 degrees relative to the original drawing, but it's nonetheless the same giraffe. So, now that you're getting the hang of thinking outside the box, let's try a different sort of puzzle. Have a look at this array of numbers. Your task is to figure out what number belongs where the question mark is. As always, pause the video to think it over. What did you come up with? Well, starting from the left, you might have noticed that 99 minus 72 is 27. And then you might have noticed that 45 minus 27 is 18. And if you got that far, then you probably got pretty excited. It looks like each number is the difference of the 2 numbers connected to it to the left. The pattern seems to continue. 39 minus 18 is 21. And that would imply that the question mark should be replaced with 15 because 36 minus 21 is 15. And if we do that, then the next number is 28 minus 15, which is 13. That's more success. But now we get the bad news. The pattern is broken at the far right of the diagram. Sadly, 21 minus 13 equals 8 and not 7, like in the array. If you got this far, then you probably thought that the 7 at the end was a typographical error. Surely I meant to put it 8, you might have thought. Well, no, it's not a typo. The diagram is correct. We've just found the wrong pattern. There's a different pattern that's consistent with every number in the array. Pause the video again if you want to try to find it. It seems incredible that there could be a second pattern that accounts for every number and not just for every number but 1. But there is. The key is to sum the 4 digits appearing in the 2 numbers connected to and to the left of each number. So, starting with the far left, we get 9 plus 9 plus 7 plus 2 is 27. And the pattern keeps working. 4 plus 5 plus 2 plus 7 is 18. 3 plus 9 plus 1 plus 8 is 21. And that means the question mark should be replaced with 3 plus 6 plus 2 plus 1, which is 12. And then we work our way to the far right of the array by noticing that 2 plus 8 plus 1 plus 2 really is 13. And 2 plus 1 plus 1 plus 3 really is 7. Amazing! This puzzle was created by Nob Yoshigahara of Japan. I can't even imagine how he came up with it. Let me set the next one up for you. Suppose you remove 10 cards from a standard deck, turn them face up, and then shuffle them among the remaining cards. The result is that you now have a stack of 52 cards with 10 of them face up and 42 of them face down. Your task is to divide the deck into 2 piles in such a way that you are certain the number of face-up cards in each pile is exactly the same. That doesn't sound too difficult, right? After all, you could just start dealing the cards onto the table until you have 5 face-up cards in your pile. But there's a catch. You have to do all of this in a pitch-black room, so you cannot see the cards as you're dealing them out onto the table. And no, you can't tell by feel whether a card is face up or face down. Now suddenly it sounds impossible, but I promise you it can be done. Take a few moments to see if you can figure this puzzle out. All right, so we have 10 face-up cards randomly distributed among a deck of 52. But we're in a pitch-black room, meaning we can't simply look at the cards to see which are face-up and which are face down. However, there are 2 things we can do even when we cannot see. We can count off a certain number of cards, and we can turn over stacks of cards. We can use that to our advantage by counting off 10 cards and then flipping those 10 cards over. Any 10 cards will do, although it's certainly easiest just to count them off from the top of the deck. Anytime you do this, deal out 10 cards and flip them over, the number of face-up cards will be the same in both piles. Let's see an example. Suppose that 3 of the cards in your stack of 10 are face-up. That means that the other 7 face-up cards are in the other pile. Now, when you take your pile of 10 and turn it over, everything that was face-up is now face down, and everything that was face down is now face up. That means that after we turn over our pile, we have 7 face-up cards and 3 face-down cards. In other words, there are 7 face-up cards in each pile. Of course, there was nothing special about starting with 3 cards in our pile of 10. We could have said there were X face-up cards among those 10. And that would mean that there are 10 minus X face-up cards in the other pile, since we started with 10 in total. When we take the stack of 10 cards and flip them over, there will now be 10 minus X face-up cards in that pile as well. Clever. Okay, last one, at least for a few minutes. Suppose you have 3 light switches. You're told that one of the switches controls a light bulb in a different room, while the other 2 do nothing. You can adjust the switches in any way you want, after which you're allowed to enter the other room a single time to see what effect you've had. How can you determine which switch controls the light? Of course, you could just randomly flip one of the switches and then enter the other room. You might get lucky and find that you guessed correctly. But if the light is not on, then you'll only know that it was one of the other 2 switches that controls the light. So you'll have to do better. Put me on pause and think about it. So what should we do about the light switches? Sometimes people treat this as a purely abstract problem, and viewed that way, it really does seem impossible. But the assumption here is that we're talking about a real light bulb and real switches. The solution is to flip up the first switch and then to leave it up for a few minutes. Then we flip it down and flip up the middle switch. Now we immediately enter the room. If the bulb is on, then the middle switch controls the bulb. If the light is off, then we carefully touch the bulb. If it's hot, then it was the first switch. And if the bulb is off and cold, then it's the last switch that controls the light. As always, it's easy once you see it. All of these puzzles require outside-the-box thinking. They have a tendency to seem impossible until you have just the right idea, and then they suddenly seem obvious. Outside-the-box thinking arises in all sorts of contexts. There's a famous story about a large truck that tried to drive through a tunnel that was not tall enough for it. The truck wound up so tightly wedged into the mouth of the tunnel that the driver feared they would need some very large construction equipment to extricate it. The way the story is usually told, it took a child to think of letting the air out of the tires to lower the truck. Nor are humans the only ones capable of being creative problem solvers. I recall reading about an experiment in which a scientist was testing chimpanzee intelligence. A banana was tied by a string to the ceiling, too high up for the chimpanzee to reach. There were materials in the room that could be stacked up into a tower. The chimp could then climb this tower to reach the banana. But would the chimp think to do it? The scientist stood in the corner of the room as the chimp looked at the various materials. Then the chimp became agitated. He approached the scientist and started pulling on his coat and pointing at the materials. The scientist followed to where the chimp was gesturing. When he was standing beneath the banana, the chimp climbed up to his shoulders and grabbed his prize. But my favorite example of outside-the-box thinking involves a classic physics problem. According to legend, it was used by a professor on an exam. The students were asked to solve the following problem. How can you find the height of a building by using a barometer? Now, recall that a barometer measures air pressure. By this we mean the pressure applied on us by the weight of the air above us. As you move to higher and higher altitudes, there's less air above you, and therefore you feel less air pressure. There's a precise equation in physics that relates changes in air pressure to altitude above sea level. The professor's intended solution was to measure the air pressure at the foot of the building and then measure the pressure again at the roof of the building. The students could then use the standard equation to work out the change in altitude, which is to say they could work out the height of the building. Apparently, a clever student in the class was unimpressed by the standard solution and decided to come up with his own. He suggested dropping the barometer from the top of the building and timing how long it took to hit the ground. From there, standard equations in physics will allow you to deduce the height. Or you could tie the barometer to a long rope and lower it slowly. When it finally reaches the ground, you simply measure the length of the rope. It's something of a rite of passage for physics students to devise ever more crafty solutions. You could stand the barometer on its end and measure the length of the shadow it casts at a particular time of day. Then you can measure the length of the shadow cast by the building. A simple geometrical argument based on the idea of similar triangles will now give you the height. Or you could swing the barometer from a rope, making it into a pendulum. By swinging it at ground level and from the top of the building, you can use standard physics techniques to measure the change in the strength of the gravitational field and thereby deduce the height of the building. If this is still too complicated, you can get really creative. Using the outside fire escape to climb up the side of the building, you can mark off barometer lengths on the wall, thereby measuring the height not in feet or yards, but in barometer lengths. Or you could simply approach the building superintendent and say, I have a proposition for you. I'll give you this shiny new barometer if you tell me how tall the building is. Now that's outside the box thinking. One of our themes for this course is that puzzles and brain teasers might seem frivolous, but they develop habits of mind that are useful in all aspects of life. Some skill for thinking outside the box is a clear example of this. Every great advance in science, medicine, technology came when someone started thinking outside the box of conventional ideas. Galileo realized the facts of astronomy made more sense if the Earth went around the sun as opposed to the other way around, and he incurred the wrath of his day's inside-the-box thinkers. But he was right. Charles Darwin based his theory of evolution on facts that were readily available to everyone in his time, but it fell to him to see the patterns that had eluded so many others. The theories of gravitation and relativity were outside the box of conventional thinking when they were first proposed, which is why it took the creativity of Newton and Einstein to dream them up. No one ever changed the world by thinking along the same lines as everyone else. To make the same point more humorously, here's a story I've always liked. A company offered its employees a large cash reward for coming up with the best money-saving idea. One employee suggested cutting the award in half. Let me close with one final puzzle. It's very difficult, and you should not feel bad if you're unable to solve it. Almost nobody does. But I've included it anyway, simply because it's really very clever, and requires some serious outside-the-box thinking. I think you'll enjoy hearing the solution, even if you choose not to spend too much time trying to solve it. Here we go. Have a look at this list of numbers. I've generated these numbers by repeatedly applying a certain rule. Your task is to determine the next number in the sequence. Now, I invite you to have a go at this right now, but if you're like most people, including me the first time I was shown this puzzle, you might quickly abandon the problem as hopeless. Take a minute, though, and give it a shot. When you come back after the pause, I'll give you a big hint that many people find helpful. How'd it go? Let's have another look at our strange sequence of numbers. I promise you a hint, so here it is. I want you to read each number simply as a sequence of digits. In other words, if I wrote 1, 2, 3, you would say 1, 2, 3, and not 123. As you read off each sequence of digits, stare hard at the number immediately above it. Got it? I'd recommend pausing here to give the puzzle a fresh look. Now for the solution. An inside-the-box approach to a problem like this would be to look for some arithmetical pattern at work here. For example, if I'd given you the numbers 1, 2, 4, 8, 16, and asked you for the next number, you'd quickly come up with 32 because I'm just doubling the numbers each time. Perhaps you spent some time looking for something like that here. But there's a very outside-the-box way to think about these numbers. The trick is to realize that each number is an exact literal description of the number immediately above it. We start with 1. That can be described as 1, 1. Hence, the next number is 1, 1. We can describe 1, 1 as 2 ones, making the next number 2, 1. In turn, 2, 1 consists of 1, 2 and 1, 1, making the next number 1, 2, 1, 1. And this number is 1, 1, and then 1, 2, and then 2 ones. So our next number is 1, 1, 1, 2, 2, 1. And now we have 3 ones, 2 twos, and 1, 1, making the next number 3, 1, 2, 2, 1, 1. And now we can solve the puzzle. Since this last sequence of digits is 1, 3, 1, 1, 2 twos, and 2 ones, our final number is 1, 3, 1, 1, 2, 2, 2, 1. Of course, we could continue this forever. If you have a mathematical cast of mind, you might wonder if we'll ever have a digit greater than 3. The answer to that one turns out to be no, but that's not easy to prove. Sequences of this sort even have a name in mathematics. They're called look and say sequences. You know, that last puzzle was really so difficult that I feel bad leaving you with it. So here's one last riddle for you. A man goes into a store to buy a certain item. The salesperson tells him the item costs 25 cents each. The man replies, "Great, I'll take 100." The salesperson charges him 75 cents for this. What was the man buying? He was buying house numbers, obviously. See you next time.